Okay, it looks like it's time to start. Can you guys see my video or just the screen?
Both. You can see
Okay,
both.
I can't see my own video, but that's fine. I don't need to see myself. For some reason, all I see is Paula's picture. Okay. Anyways, okay. So today I'm gonna talk about adders. We started that last time, but we really didn't get very far. So adders are kind of an interesting thing to look at. I think most of you will probably never really design an adder yourself, but the principles that we use in designing fast adders are principles that can be applied to other types of circuits. Also, adders are a really good example of how you trade off performance for cost. So that's why I like to talk about them here, because the principles are kind of general, even though these days adders are kind of built for you automatically with the tools. So last time when we started this, I kind of reminded you about the idea about using trees for reductions. So if we have operators that are associative, then we can, and we have a reduction to do, we can put things in the form of a balanced binary tree, and this gives us kind of the minimal delay. We get a delay that's proportional to the log of the number of elements that are being, the number of inputs. And that's a good thing because that makes our circuits go faster, right? And then I also introduced this idea of the special type of tree called a parallel prefix. And this is a tree where we're interested not in just the final result, the reduction of all the inputs. In this case, we're using the plus operator, whatever that is. That could be add, or it could be or, logical or really any associative operator. In this case, in the case of the parallel prefix, we're interested not just in the final result that comes out here on the right, but all the other kind of intermediate results. So the final result is A ANDed with everything up to x15. I'm sorry, x0 all the way up to x15. And then we get all the intermediate results out as well. So x0 plus x1 and x0 plus x1 and plus x2 and x0 plus 1. Plus 1 plus x2 plus x3, etc., all the way up to the reduction of everything. Okay, so that's parallel prefix, and we'll use that later in the design of a special type of adder. That's why I introduced it here. Okay, so first of all, I want to do a little review of just basic adder principles. And so this we've seen earlier, and you probably saw in other classes. The way we motivate the design of an adder is we look at what we do by longhand addition. What we do, and with longhand addition, we normally are doing it with decimal numbers, but it's really the same with binary numbers. So we start on the right and we add the two partial, the two digits, in this case, the two bits that are in the rightmost column. We get a result and possibly a carry. And then we take the carry over here and we add it in with those other two, and we get a result and possibly a carry. We just continue this from right to left all the way through the word, and we get the final result, bits, and then possibly a carry out at the top. Okay. Now, if you could just enumerate all the possibilities that can happen at each stage here. Now, in this little example, I showed you the rightmost stage as being special because there's no carry in, but we can just generalize that and use the same kind of logic for every stage and assume that perhaps the carry in is 0 in the case of addition. Right now, if we do that, then we look at each stage. What we have is a function, two functions of 3 inputs. Get the carry in, the A bit and the B bit. We get a result bit and a carry out. Right? And we looked at this before. We enumerated all these possibilities in the truth table, and then if we apply some, well, in fact, what we did is for the carry, we did an algebraic proof showing that the carry out is BC or AC or AB. We can also look at that with the Carnot map. It was much easier. So we got that function that way. And then we know that the sum function, by inspection, you can see it's just the XOR of the 3 inputs, A, B, and carry in. And then from that, we can derive some circuit level representations. Here's one version here. It's not unique. We could factor a little bit and end up doing things with 2 input gates. as shown here on the right. In this carry out expression here, we factored out C in. And then we can, this gives us a 3-level logic, which we can do with 2 input AND gates. Okay, now once we have that, then we can string these cells together to make the full adder. I'm sorry, the ripple carry adder. We string together the full adder cells, and this gives us a way to build an adder. Okay, so what we want to do today is kind of take this basic idea and improve on it to make it faster. I'll be showing you some techniques for that. Before we do that, though, I want to look at subtraction because, often, for instance, in the ALU of a CPU, not only do we need an adder, we also need a subtractor. And since it's related, we should be able to kind of borrow some ideas from an adder in order to make a subtractor. So one way to design a subtractor would be to go through the same steps that we just went through here, except change the truth table. Instead of putting the truth table in for addition, we could put in the truth table for subtraction. And instead of getting a carry from one stage to the next, we get a borrow. Right? And that's a perfectly legitimate way of doing things. There's another way to do things. If you already have an adder and you'd like to make this adder be a multi-purpose block, so it could either function as an adder or function as a subtractor, then we have another way of doing that. And that's what I'm going to show you here. And so the idea here is if we want to do A minus B, if we want to perform A minus B, we can perform A minus B by adding the negation of B to A. Right? It turns out it's the same thing, as you might suspect. And so how do we form the negation of B? Well, we're assuming these are 2's complement numbers, and we know the formula for doing that. What we do is form the complement of B, the 1's complement, which means we just invert all the bits of B, and then we add 1 to it. And that we know gives us the negation of a 2's complement number. Right, so we can do that in the circuit conditionally based on whether or not we want to do an addition or subtraction operation. Right? And the way we can do that I've shown here. So the bits of A go into our adder as normal. Here's an n-bit adder, and this could be any adder architecture. It could be a ripple adder. It could be anything. So what I'm showing you here is a way you could turn any adder into a subtractor by just changing some things on the outside. The B bits we want to conditionally invert. Right? So if we're going to perform a subtraction operation, then what we'd like to do is invert all the bits of B and add 1 to B. Well, we can conditionally invert by using XOR gates here on B, because if you look at the XOR function, it's really a conditional inversion. I think we talked about this before. So we have this sub control signal here. If sub is 1, then when B will get XORed, B0 here will get XORed with 1, and that will result in the inversion of B. Likewise for all these other bits. So this gives us a way to conditionally invert B. And then the +1 comes in here, this carry in. If we assume that carry in is not 0, but it's something we can control, right? And we know how to make an adder like that, then the sub signal can also be used as an input to the carry in. So if sub is 1, we assume the carry in is 1, which means that will add 1 extra 1 to the rightmost stage of this adder, right? Which is, so nice thing about adders, if you make them out of, as I showed on the previous slide, out of full adder cells, you get an extra input here, which we can use to get a +1 for free, right? So that's the trick here. So this is a way to make any adder into a subtractor. Okay, so now I'm going to move on and talk about, kind of motivate why we want to move away from ripple adders. And the interesting thing about ripple adders in particular, in most combinational logic circuits, we talk about the critical path, right? Determining the kind of the worst case, which is the worst case delay through the circuit, and that's going to determine the maximum clock frequency that we can use the circuit at. In the case of adders and a lot of other circuits, the actual length of the critical path is dependent on the data inputs, right? So for instance, if you look up here at this little illustration labeled T0, we have a 4-bit ripple carry adder here. And if we put inputs in, if we put A the A input is 1, 0, 0, 1, and the B input is 0, 0, 0, 1. And we apply those to the circuit. What's going to happen is we'll get a 1 out of the cell on the right, we'll get a zeros out of the other cells, and there's no carry, right? Because 0 plus 1 plus 0 is 1 without a carry. Likewise, at each other stage, there's no carry generated at all. So the result will come through very quickly. It'll come through in the time that it takes for the full adder to do its function. We don't have to wait for any ripple carry, right? Likewise here, even if we change the input, A is now 1, 0, 1, 0, and B is 0, 1, 0, 1, you can see there's also no carry in this case. So that result will come out quickly. However, if we change the input, let's see, from what we had on T1 here to T2, over here, we look at 1, 1, 1, 1, and we add a 1 to that, 0, 0, 0, 1. What will happen in this case is we'll get a 0 for R0, and we'll get a carry. It goes into this cell, and it adds with that 1, and we get a 0. Right? But I'm showing it down here actually in T3. What will happen then at a later time, eventually this 1 will go over to here, add with that 1, we get a 0 out here and a 1, carry. Carry goes here, adds with that 1, we get a 0 for a result and a 1. Right? So we're going to see, we exercise this bad path, this long path in that case. And in fact, there's some subset of all the possible inputs that will exercise this carry. Sometimes the carry will just come halfway and then it'll stop. Sometimes the carry will exercise a propagation of the carry all the way to the end. And it's in those cases where this adder has its worst case add delay. And because of the way we design synchronous systems, we have to allow for the worst case because it might come up. We can't take advantage of the fact that sometimes this adder will have get a result in a shorter amount of time. Right? We have to allow for the worst case, and that's what gives us the critical path. And it always gets exposed for some inputs. I showed you one here, but there's others. Okay, so what this means then is a ripple adder is inherently slow because of this. In the worst case, this S7 output, the sum out of this adder here, has to wait for C7. It's not uniquely determined until C7 is stabilized, and C7 doesn't stabilize until C6 is available and all the way down the line. All right, so you get this long dependency. All right, so what this means is for ripple adders, the delay through this is proportional to n. Worst case, we have a carry that goes through all n cells. And the cost of this is nice though. I mean, the cost is linearly proportional to the number of bits. So if we scale the size of this adder, it only grows in complexity linearly with the number of bits. Okay, so we say the cost is also proportional to n. In particular, the cost here is n times the cost of a full adder cell. And that roughly would determine how much area it would occupy on a chip. So how do we make it faster and perhaps with more cost? I can tell you now, of course, the only way to make it faster is to add more logic. So we're going to look at ways to do that. So before I do that, let's kind of motivate the design and the next kind of idea that we're going to introduce here. And if you look at what makes this adder slow, it's the fact that we have this long carry chain, right? There's a critical path that snakes through all these cells. So the only way we could possibly, or one way we could think about speeding up the circuit would be to cut this path somewhere, right? So the signal doesn't have to propagate all the way to the end and kind of decouple, have one signal that propagates in the top half and another signal that propagates in the bottom half, and they can both go at the same time. Right. But how do we cut it? If we cut it here, we don't know what C4 is. Right. So we could make a guess. We could just say, well, let's assume C4 is 0. Right. Now, sometimes it is. So that adder, sometimes it would produce the right result, and sometimes it would produce the wrong result. Right. So, in fact, probably most of the time it would produce the right result, but we really don't find this very useful because we need an adder that's correct all the time. We're really not interested in approximate addition. We want exact addition. So if we're going to cut the carry chain, we need to be more careful on how we do that. So one way to cut the carry chain would be to cut it here and then replicate the top half of this adder structure, we'll have one version that computes as if C4 was 0, and another version that computes as if C4 were a 1. We can make both guesses and then choose later based on what C4 ends up being eventually. Okay. So that's the approach here in something called a carry select adder. So what we're going to do is select between two different versions of the top half of the adder based on the carry coming out of the bottom half. So you can see how this works. So we took the structure I had on the previous slide, which was an 8-stage carry ripple adder. Cut the carry chain at this point. Okay, replicate the top half. These two are the same. And then what we do is the top one, I've replicated the left half. The top one assumes that the carry in, or C4 in this case, is a 0, and the bottom one assumes that the carry in is a 1. So we compute both versions of that, right? And then we choose the proper version based on what C4 actually ends up being. Right? Likewise, we put another multiplexer here that can multiplex out and choose the proper version of C8 out of either the top or the bottom. Okay, and you can see why this speeds things up, because what can happen is the top half, these two, can ripple in parallel with the bottom half. All right, so they'll both take their time and ripple through, stabilize, and then at the very last minute, whatever C4 is coming out of the ripple from the lower half here, we can use that to choose the proper result for the top bits. Right, so we'll see the bottom bits come out, this carry comes out, and then very quickly thereafter, because there's not much delay in the multiplexers, we'll see the top bits S4 through S7 come out. All right, so this is kind of a clever idea. I think it's a generally useful idea, which you can do in hardware. You can kind of compute both possibilities and then choose at the last minute which one is the correct one. This is a principle that's called speculation, because we're speculating on what the result will be. In fact, we compute two possible outcomes and then choose the proper one. So I hope you understand this principle. It's kind of a simple idea, but it's pretty powerful. You can see what the effect of this transformation is then on the adder circuit. In this case, the time now. So previously we had that the delay was going to be n times the delay through a full adder cell, through one of these cells, because we had to ripple n times. Worst case. Here, the worst case delay is going to be the time of the ripple adder that we had before divided by 2, plus the delay of the mux. So if we can assume that the mux delay is relatively small, we have approximately doubled the speed of the adder with this technique. And of course, it came at the expense of more hardware. In this example, we pretty much double 1.5, 50%. We duplicated all at the top half of the adder, so the cost is pretty much 1.5 times the cost of the adder. Plus, we had n over 2 plus 1. Here's the n over 2 muxes plus 1 more mux, so we'd n over 2 plus 1 mux times the cost of a mux. Right? So basically 50% more cost plus the cost of the mux will give us a speed up of approximately 2x. That's a pretty good trade-off. Okay, so if you like this idea, you can extend it and things actually get a little better. Here, this is an extension of this idea. So the previous one, I just cut the adder in half. Here, we cut it into 4 pieces. I'm demonstrating it here for a 16-bit wide adder, right? And we have kind of 4 blocks then. The low block is just a 4-bit adder. And then each block kind of looks like what I had in the previous slide. So what we do is take that range of bits. Let's see, so the next block over, we're looking at bits 4 through 7. Okay, so the A bits and the B bits go in. They both go into 2 4-bit ripple adders here. But again, the top one is initialized with a 1 and the bottom one is initialized with a 0, meaning we assume the carry in is a 1 there, assume the carry in is a 0. And then we have the multiplexers here that can choose the proper result. So these result bits are chosen based on the carry output of this low block here, right? So that controls those multiplexers and also controls the carry going to the next block, right? Which is going to be the carry out of these two 4-bit ripple adders here. Okay, and that gives us the carry into this stage, which then can be used to control those multiplexers and that multiplexer, and that gives us a carry out, which controls those and that, right? So this should be approximately 4 times faster than a ripple adder that's 16 bits wide, because we got 4 blocks all operating in parallel here. It's not exactly 4 times faster because we have to wait for kind of this propagation of this carry signal here, right? Because it comes, we wait for the ripple here, and then the signal, the critical path is going to be through those full adder cells, then along this wire, through this multiplexer to get a signal out. Then this signal, this carry comes over to here, and we have to control that multiplexer and get another carry out, and control that multiplexer and get another carry out. So the critical path is going to be the combination of going through the ripple of the 4-bit adder and then moving through those 3 multiplexers. Right. Now, you can ask the question, and then if we're going to take this approach of cutting an adder up into multiple blocks, what's the optimal number of blocks and the number of bits per block, right? So if you think about this a bit, I mean, we could formulate this as an optimization problem and find the optimal, but it's sort of obvious. There's really just a trade-off between 2 things here. So we need to balance the 2 things. The 2 things are the delay of this ripple, initial ripple, and then the delay of these muxes. So if the blocks are too small, then the delay gets dominated by the total mux delay, right? If the blocks are too large, then we get dominated by the adder ripple delay. Right? And it's just the sum of the 2. So the some kind of quadratic optimization, right? Because you just trade one off for the other. So that means the optimal should be when you have equal delay due to muxing, which is equal to the delay that you have due to the ripple in the initial ripple adder here, right? Okay, so that ends up being square root. So if you have, assuming that the delay through a mux is about the same as a delay through a full adder cell. So you want the number of bits in this full adder here to be about the same as the number of mux delays you have. Right? So that would be square root of n. Okay, so then you end up with a delay through the whole adder being proportional to the square root of n. It's something like 2 times square root of n times the delay of a full adder cell. And then the cost, it will be approximately, you can see if you have a lot of blocks, you approximately double the amount of a hardware plus add that the muxes. So this is the approximate cost here, 2 times the cost of a ripple adder plus the cost of the muxes. And like I said, the delay is proportional to the square root of n. And this, for this style of adder, this is a very common place to stop. But I'm going to show you one more optimization on the next page. Okay, so here's our carry select adder with square root of n blocks of each one square root of n. In this case, this is fairly optimal because square root of 16 is 4. So we have 4 blocks of 4 each. Just to quickly compare it to the ripple adder delay, we can see that so the delay, the total delay here is going to be 2 times the square root of n times the delay of a full adder cell minus 1, assuming full adder and the delay of a mux are about the same. So we're going to get, like I said before, n delays here, and then ends up being n minus 1 delays through the muxes. So that gives us the 2 times square root of n times t sub fa minus t sub fa. Okay. If you look at this compared to the ripple adder, which had a delay of n times the delay of full adder cell, here's the delay of the ripple. So the crossover point is n equals 3. So what this says is the carry select adder is faster than a ripple adder for any value of n greater than 3. Right? So pretty much it's always faster than a ripple adder. All right. Now, is square root of n really the optimal? Well, it's not really the optimal. It's pretty close to the optimal. You can do better. And let me motivate this, explain this down here in a minute, but let me just say, if you look at what happens as the circuit is running, you put all the inputs in. We have a ripple going through this cell here. In the meantime, while this thing is rippling and stabilizing, all these other 4-bit adders are stabilizing as well. So this one stabilizes and then just waits for this signal to come so it can send its carry to the next stage. In the meantime, this one is just waiting until it can send its carry to the next stage, and likewise here. So this one waits a little bit on this. This third stage here waits longer than that one. This one waits even longer, right? So these stages get done early. So we're kind of wasting a little time. They get done early and they're just sitting there, right? So we could put a little more work into each block or each stage, if you call it, as we move from right to left, right? So we could make this 4-bit adder a little wider, right? Make this one a little wider than the 4, make this a little wider, make this a little wider. Okay. If you do that, perhaps you can end up with fewer blocks and less overall delay. So it doesn't work out well on small adders, but for large adders, for instance, a 64-bit adder, if you use block sizes that are like this. So my simple thing before we said use the square root of n for the size of the number of blocks and the size of the blocks. Square root of 64 would be 8. Okay, so that would be a perfectly fine carry select, but you can make it more optimal if you size the stages like this from right to left, 7, 7, 8, 9, 10, 11, 12, right? And that balances the delays better. You don't have a stage or a block here finishing, it's rippling and then just waiting for the carry signals to make it over to it. You can give it a little more work so that all the signals kind of come together at just the right time. And circuits that balance the delays, in other words, where most paths are close to critical, tend to be more efficient. Right? In this case, if we do this with a 64-bit adder, we have blocks as shown here in the square brackets, we end up with 1, 2, 3, 4, 5, 6, 7 blocks instead of 8. Right? So the whole thing is going to be a little faster. All right, so the exact kind of configuration for the size of the blocks kind of depends on the total size of the adder and the relative delay of the mux and the full adder. Here we assume the mux and the full adder are around the same speed. Okay, so that's all I wanted to say about carry select adders. So this is a type of adder that is relatively inexpensive in terms of hardware, but significantly faster than a ripple adder. It's not used a lot these days. It's used in applications where somebody needs a relatively fast but relatively inexpensive adder. Most adders use another technique, which I'm going to introduce next, called carry look ahead. And it's actually the two related concepts here, carry look ahead and adders that use parallel prefix, which is what that idea I introduced earlier. So the carry select adder we just looked at had a delay proportional to the square root of n, which is much better than n. But really what we would like is a log. We'd like a delay proportional to the log of n. Because for large numbers, log of n is better than the square root of n. Right? I mean, even think about it for 64. Square root of n is 8 and log of n is 6, right? And it only gets better as we get to larger word widths. So we want to kind of figure out how to build adders with a delay proportional log of n. If you think of, so the real problem with adders is the carry generation, propagating the carry all the way to the end. But the carry is actually needed all the way along the end, right? Because we need that in order to generate the sum, because the sum was the XOR of A, B, and the carry in. So to generate the sum bits along the way, we also need the carry. We can't just generate it all the way at the end. We need to generate it all the way along the carry, right? So that's why we look at possibly using a parallel prefix. This was the computation that I introduced earlier. It was the tree that generates a final reduction, but also all the intermediate results. If we could do this, if we could figure out how to create the carry signals all the way along the adder using a parallel prefix tree, then we would have an adder that had a delay proportional to log of n, and that would meet our goal. But parallel prefix or any kind of tree, balanced tree type computation requires that the operation be associative. And the simple carry generation, as we've been looking at it up to this point, for instance, what we looked at in the ripple adder, that carry generation is not associative. We can't just turn that into a tree. It won't work. Okay, but we can arrange carry generation to be associative. And that's what carry look-ahead adders do. They reformulate the way that carries are generated. And I'm going to show you how we do that. So this is kind of the key thing. We reformulate the basic adder stage into something that looks a little strange at first, but you'll see how it works later. Okay, so here's the truth table for a single stage of an adder, right? Just as you might have in a carry ripple adder, or as you might have if you did longhand addition. So there's A, B, and the carry in, that's C sub I. And then we have the carry out of the stage and the sum out of that stage. Right? And I've divided it into 3 sections here with these dashed lines. And you can see that if you look at, we're interested in the carry signal here, and you can see there's interesting sections here. Here the carry is 0, regardless of what the inputs are. And here is the carry is a 1, regardless of the inputs. And then here, the carry out is just equal to the carry in. So we can use that as a different set of logic equations for making the carry. And traditionally, this is called the carry kill section. This is the carry propagate, and this is carry generate. It's called carry propagate because the carry out, this is C sub I plus 1, is just the same as C sub I. So we just propagate whatever the carry into that stage is, we're just going to pass it on through. And then there's the carry generate here, regardless of what the carry in is, the output of this stage, the carry out will be a 1. Likewise here for carry kill, regardless of what the carry in is, if we're in this section, then the carry out is a 0. So we could make the carry signal by noticing which section we're in. And we can notice which section we're in by, if you look here, A and B are both 0. Here in this section, A and B are both 1. And then here, XOR of A and B is a 1. So that's these equations here. So we know we want to propagate a carry if AI XOR BI is true. So propagate will be true if A XOR B is true. And then we know we will be in the generate situation. We would want to generate a carry if A and B are both 1s. Right. And it turns out we only need propagate and either generate or kill. I just like doing things with generate, so we're going to use generate and propagate. Okay, so that gives us kind of a new way to think about doing carries. So we can take these equations and combine them in this way we can say then that the carry out of a stage is equal to the generate of that stage or propagate and the carry in. So the way to interpret this says if we generate a carry, then if the generate signal is true, then output, the carry out is going to be 1, or it'll be a 1 if the carry in is a 1 and the propagate is a 1. Right. So if propagate is true, we just pass carry through. It's either a 0 or a 1. And then if generate is a 1, we generate a 1 regardless. And then the sum, as we know from before, sum was just the XOR of the 3 inputs to a stage A, B, and carry in. So we can just reformulate that using P. Since P is A XOR B, then sum is P XOR C. All right, so that gives us a new set of equations for the carry out and the sum out of a stage. And we have these kind of intermediate results that we can use to feed these equations. Okay. So what I've shown here is we can reformulate then the ripple adder using the propagate and generate signals. Okay. Now, I'm just showing you then the kind of the principle. We actually don't build adders this way, but it's useful to understand this. So again, these are our two propagate and generate signals. So we could have a block that combines A sub I and B sub I and generates P sub I and G sub I. So we do that at every stage. These run then into a block that has a logic for making the carry based on a carry in and making the sum based on the carry in and P and G. Right? So P and G feed into here, get carry in, we get a carry out, we get a sum out. And do that for every stage and just string these together just as we did with the carry ripple adder. And we'll get effectively carry ripple adder that's just kind of uses a different set of logic equations. There's really no advantage here over a ripple adder. It still have proportional delay proportional to n, but it just kind of demonstrates the point that this is a perfectly fine way of making carry by using these P and G, the propagate and generate signals. But obviously we did this because these P and G signals have nicer properties, nicer algebraic properties, and we can use that to our advantage for making circuits that are more tree-like. Okay, so a way to think about making better circuits is by the fact that we can apply some hierarchy. We can kind of group, propagate, and generate signals together. The trick to making trees is to kind of figuring out a way to make a hierarchy, kind of conquer and divide. And we can do that with these P's and G's. So let me show you how we might do that. Here's a set of P and G blocks here. We're assuming the A's and the B's are coming in on the left here, and I'm just showing the P sub I, G sub I for, from I up to K. Now, we can say that we can form this super P signal and the super G signal. This is a P that operates over a whole set of sub blocks, right? So this says this big P is true if it's the and of all the individual P's here, right? Because think of this as a group. If we can propagate a carry all the way through this whole group, if the propagate signal of every subcell is a 1, right? So that's the and here. And then we can ask the question, how would we generate a carry out of this group here? Well, the group generate would be, well, either this bottom block, the carry, I'm assuming the carries are coming from top and going down to the bottom here. We can generate if there's a generate is true in the bottom stage here, right? Or the one above it has a generate and then a propagate, and then it propagates through this, right? Or somewhere in here, we generate and we propagate all the way to the output, right? So that's this equation here. It says big G is equal to G sub I plus K, or G sub I plus K minus 1, that's the previous stage, ANDed with propagate of this state, the final stage, p sub I plus k, right, et cetera, all the way to where this is this condition where we generate out of the top stage and propagate it all the way through. And that's this final term here. Right. So what this tells us is P is true if the group as a whole propagates a carry to C out, and G is true if the group as a whole generates a carry. Right. And then we can apply this equation, which is kind of a meta version of what we had before. It says C sub out. It's the same kind of thing. We say C sub out is equal to G or P times C sub in. Right. So if we have C sub in coming to this block, we can quickly generate C sub out, right? Assuming we can generate all these intermediate, generate the big P and the big G. Yeah. And I'm going to show you we can do this kind of hierarchically so we can make it go fast. All right, so that's the basic idea behind, really, that if you understand this idea, this is the basic principle behind all carry look ahead, all adders that have a delay proportional to log, or not all, but all that use this P and G type signals. Okay, so let me show you that. Here's an example of how we put this to work in a 9-bit adder with hierarchically generated P and G signals. So this 9-bit adder I cut up into 3 sections. The low section is at bits A0 through, or bits 0 through 2, and then 3 through 5, and then 6 through 8. We assume inside each block here, the A, B, and C block, there's we generate P sub A and G sub A, right? And that's just what I showed on the previous slide. It's the and of what we would do internal here. We would generate a P sub 0 and a G sub 0 and a P sub 1 and a G sub 1, et cetera, et cetera. And then we combine the P sub 0 and the P sub 1 and the P sub 2 to make P sub A, right? And then we would also have a circuit that generates all the individual G's, and those G's would get combined along with the P's, and we'll get G sub A, right? Likewise here and here. And then at the next level up, we could make a super P, which is P sub A times P sub B times P sub C, and we can make a super G, another big G for the whole 9-bit adder, which is G sub C plus G sub B times P sub C, right? Plus G sub A times P sub B and P sub C, right? So these are the 3 different kind of big conditions under which we can get a generated carry. Could be we generate it in this block, or we generate a carry here and propagate it through, or we generate it here and propagate it through, right? Once we have these, we could use this P without a subscript and this G without a subscript, and we can generate C sub 9 directly from C sub 0. So C sub 0 is the one that comes in all the way over here. Right? If we have these 2 signals created, then we could use this same equation we've been using all over again to make C sub 9 very quickly based on C sub G and C sub 0, and then the G and the P. Right. So this thing would kind of, all the inputs would come here, and then the P and G signals would propagate to the right. And once we have these if we needed C sub out, we could generate it quickly from C sub 0. These intermediate carries are generated as shown here. C sub 3 is a function of C sub 0 and P sub A and G sub A. And then C sub 6, which is needed into this cell here, can be generated with the P and the G from this stage, along with the C sub 3, which we can get from there. We need these intermediate carries at every stage because the sum result, which I'm not showing here, we can imagine the sum kind of flows out of the left. Those sum bits all depend on the carry at each point along the adder. So we need to, even though we'd like to quickly make the carry out, we also need carry everywhere along the way to be generated quickly, because we combine that carry at each stage along with A and B at each stage to make the sum bit. Okay, so that's one type of adder. I'm going to show you another example. This is kind of does it in groups of 3. This is a radix 2 version. It does it in groups of 2. And here's 8-bit one. And I wanted to show you this because I show it in great detail. So if you're not following everything I'm saying now, you can go back and look at this one later and see if you can understand it. And I think you should be able to understand it. So the way to look at this, it looks kind of complicated, but there's 2 different types of cells. There's actually 3 different types of cells in here. We got the cells on the left. The cells on the left, the square ones, what they're doing, they take A and B and a carry in, and they make a sum out, and they make a P and a G signal. Right. So this is all the kind of equations we've been looking at previously, where we get the P and P sub I and G sub I based on A sub I and B sub I. And then once we have those P's, we can, based on the carry in, we can make a carry out. Right. And some of the cells don't have carry out. They don't have the dash, the kind of slash through them. The rest of this tree is made out of these kind of combiner cells, and they take 2 sets of PG signals, and they make a super P and a G. So it's just like what I've been telling you in the last couple of slides. And then the ones that have the dashes slash through them also use that P and G to propagate the carry down here. And so you can see we kind of built up this tree in this hierarchical way. At the very top, we get a P and a G here. We have the sub PGs all the way along the way. We can use the sub PGs as needed to generate, generate these internal carries which propagate back through the cells this way. So if you look at the kind of the propagation of signals through this, when we apply the A and the B, our 2 inputs, what will happen is P and G signals will propagate to the right, first through that set of stages, blocks, and then through that set of blocks, and then eventually to the root of the tree. Right. In the meantime, carry signals will kind of propagate backwards back towards the leaves of the tree, right, and get distributed through here, and then the sum signals will come out. Right. So roughly speaking, what's happening here is that we get a wave of evaluation from the leaves of the tree to the root, and then from the root area, basically from here and from here and here, the carries kind of move backwards back through the tree, and then the sums come up. So this gets a delay that's, you can see it's going to be proportional to log, because this tree structure here is going to be proportional to the log of the number of leaf cells or the number of inputs. In particular, in this case, you're going to get like 2 times log of n times the delay through one of these blocks, which will be the delay. So the critical path is 2 traversals of the tree, one for the P's going to the PG's going to the right, and one's for the carries going to the left. So I think the critical path ends up being something like, as I'm tracing out here, up there, and then through C, and then through that block, and then through that block, and then into that block here, and then a S sub 7 comes out, which somehow got dropped out here, right? So that's a carry look ahead adder, and this particular one is radix 2. Anybody want to ask anything about this? I know it's kind of a hairy looking structure. It's not so bad once you look at it, take your time and carefully understand it.
I got a quick question.
Sure.
Wouldn't it be the delay greater than the other technique we previously looked? Because for the A to B to S2 block, they need to wait for the carry from the greater PNG. So this tree structure needs to wait for that carry. Wouldn't it be greater than the other
the carry select adder?
Yeah.
It might be for this size adder, for an 8-bit adder, because there's but asymptotically it's faster. So if you looked at a reasonably sized adder like 16 bits or 32 bits or 64 bits, this one would definitely be faster.
Oh,
Because
okay.
that one has, this the square root of, the worst case is going to be the square root of n, and here it's really going to be log, because you get a log to get to this point and then another log to go back. The way I did ripple it a little bit here, you might be, yeah, no, I don't think you can do any better than that. But yeah, uh, asymptotically, it's faster, and I don't know what the crossover point is. That's a good question. That would be a really good homework problem, is crossover point between that one and this one. And I think you're probably right. I think this is probably slower for 8 bits. Okay. Anything else? All right, I'll move on. Okay, so this is your classic traditional carry look ahead adder. And then here for your information, I wrote out all the equations that appear everywhere in this 8-bit adder, and you can see all the details here if you want it. Okay, now I'm going to move on. So the rest, well, not the rest of the time, but I'm going to move on to the next class of kind of fast adder that uses a carry look ahead technique, but it's formulated slightly different. This one is actually more popular and more common these days. The one I just showed you was a little old fashioned. So it's going to use this idea of the generate and the propagate signals. And first, let's just go back and look at if we started enumerating all the carries along the way. Because really our problem, we've reduced the problem to finding a way to quickly generate these carry signals. So if we assume C0 is a 0 for now, and then C1 from this formula, remember it's G plus P times C. It's going to be this G sub 0 plus P sub 0 times C sub 0. But C sub 0 is a 0, so this ends up being just G sub 0. And then we can continue the C sub 2 then is this formula based on C sub 1, P sub 1, and G sub 1. But we know what C sub 1 is, so we could plug that in, get G sub 0. And we can keep plugging, and we get something that shouldn't look too strange to you. We can see that C sub 4, it kind of just, the expression here enumerates all the ways that C sub 4 could be a 1. It's either a G sub 3 or a G sub 2 and a P sub 3, or a G sub 1 and then the product of those two, or G sub 0 and the product of those three. Right. So what we can do is take this and we can kind of refactor this similar to what I showed you originally with the P and the G operator. If you think of this, the creation of a G and a P signal based on this is the binary version of it. I showed you in the previous slide the binary version, and the first one I did it with groups of 3, but we can treat it as a binary operator where we can take a P and a G and a P from the right, and a G and a P from, let's say, straight down, thinking of carries moving from right to left, and we can make a G and a P based on those using these formulas here. So G is G double prime or G prime P double prime, right? This is kind of what we've been looking at before. It will generate if we get a generate here or generate in the cell to the right and a propagate at this point. And then the P, again, is just the AND of those two P signals. So this is an interesting operator. It turns out that it's associative. So if we use this as a way to decompose this set of carry equations, we can make any kind of tree that we want, pretty much. It's not commutative operator, which is kind of strange. Most operators we know about, like and or plus, they're associative, but they're also commutative. This one's not commutative. There's this order built into it, so we have to be careful about the kind of trees we build. But we can have a lot of freedom in how we do this kind of reduction operation, how we can form these functions. And in particular, we're going to use this operator to form a parallel prefix tree. This is the kind of tree I showed you before, and that will give us a parallel prefix adder. Right. So here's a small example of how we might put this together. So I left out some of the details here. We're just coming into the top with the P and the G signals from each individual pair of bits, right? And we know how to generate that from before. What I'm showing you here is just how you combine these to generate the carry signals along the way. So here's a kind of a tree. So we know at this point we can, C1 is just the same as G sub 0 at this point. We could generate C sub 2 if we have C sub 1, which we do because we have G sub 0, yeah, it comes in here, and then the P and the G at this stage. Right? So anyways, let me just say what we do is we use these operators, we put them here, and we can combine them as shown here. So for instance, this one here, we're combining this P and this G comes down here with this G0 and P0 here, and we get this equation here. And if you work that all out, that's exactly the same as C3 sub 3, which I showed. The G is the same as C sub 3, which I showed on the last slide. Likewise here for C sub 2. So it's really just a way to kind of factor and group those set of carry equations and form it into a tree. And this one at the end here, I show the algebra here, but it all works out to be the same as the C sub 4, which we had on that page. Right. Okay, so, and then once we have the C's here, we can generate the sum bits by using this equation, which was just the local P, the P sub I, plus the carry into that stage. Right? So we could generate the sum based on C sub 2 here, and the P coming down at this point, or this P sub 1 at that point. So this gives us everything we need to make a full a big adder. And people have played with different kind of configurations for these reductions. You can kind of do these in different orders and different kinds of trees, and I'm showing you that here. So each dot is one of those operators. This operator is shown here in the upper left, right, where you just propagate the P and the G signals, right, or create the P and the G signals, right. The stages at the top, the ones, the circles here are where we generate the P sub I and the G sub I, and this kind of flow down, and they get combined. And then the outputs here are the sum outputs. So because this is associative operator, all these trees, algebraically, they're all the same if you push through the math, but it's kind of combining things in different orders, associating things in different ways. And the reason we have different versions of these is that they all provide a different trade-off between cost and performance. So this one is the most famous, the Kogi-Stone adder. And this one has minimal logic depth. So if you look here, you can get through in of the purple ones, 1, 2, 3, 4 stages of purple. And it has minimum fan out, right? Remember when we talked about fan out and logic delay, if a gate has to feed a lot of other gates, there's going to be a lot of capacitance on its output. So it'll slow down the signal path there. So this one has the advantage, it has minimal fan out. Each cell only drives at most 2 other cells. So this results in a fast adder. There's only 4 stages here, but there's less logic delay on each path. Right, so that's the fastest adder, but it has a large area because it has a lot of cells. This one to the right, this is also has minimal logic delay, but it has large fan out requiring up to and over 2 different cells. Each cell, you can see here, for instance, this cell where my cursor is, it's got to drive its signal all the way to those other ones. So you can have longer logic delay between stages here, but it's minimal logic depth, and kind of a small area. So that's a kind of a different point in the trade-off. Here's the Brent Kung adder, which has minimum area. It has a minimum number of these operators, but it has high logic depth. It has more. You can see we have to go 1, 2, 3, 4, 5, 6 possibly, right? So it's a longer logic delay here, but it's minimal area. And then here is a hybrid that combines the properties of both, right? So people have studied these things. There's lots of papers written on different adder configurations, but they all kind of are based on this principle of the hierarchical generation and of P and G signals. Okay, so here's a wrap up on carry look ahead techniques. So this is an adder that has a delay, which is O of log of n. Okay, so as you know, the O notation takes away the constants out in front. So it's something times log of n, right? So it means it's proportional to log of n, and that's a good property. So asymptotically, the delay is log of n. The cost, interestingly, well, you can make trees. We know that the cost of a tree is proportional to n, where n is the number of inputs. Right? The delay is log of n, but the cost is n. So the cost of this adder is n, order O of n. So the other thing is this can sometimes adder techniques are combined. So we can combine this with other techniques. So you could use the group P and G signals can be generated for subadders and kind of sent to subadders to quickly move the carry between subadders. But then another technique like carry ripple can be used within a block. Right? So this is used on FPGAs, for instance, where there's, as I'll talk about a little later, there's fast ripple carry blocks. Like up to 32 bits is fast. But then we use a carry look ahead structure to extend ripple adder to be a bigger size. So we could have sub adders that are say 32 bits, and each sub adder gets its carry in from the carry look ahead tree. Okay. So it gets the carry to the higher order blocks quicker than waiting for it to move through all the sub blocks. So sometimes we see combined adders, hybrid adders. Okay. Now, I'll say more about this adder cost a little later. Okay, I'm going to show you one other type of adder, which is kind of the other extreme. This is an adder that is minimal in area and as slow as you can make it. Right, so here's a bit serial adder, and this is a really kind of interesting adder too. For now, let's assume that we're going to add A to B, right? And this is n-bit numbers. You have A in a shift register here and B in a shift register. And remember what a shift register is. It's a register that every time we clock it, all the bits just move to the right in this case. So every time we clock it, we get a new bit of A and a new bit of B, right? Those bits go into a full adder cell, a single full adder cell here. So we add the 2 bits of A, add the bit of A to the bit of B, along with whatever carry we have stored from last clock cycle. Right. Initially, this is set to 0. So when we're on the right side of A and B, the least significant bits, we just add those two together in the full adder, get the sum bit, it goes into a shift register, and the carry goes into this flip-flop, which just holds it over until the next clock cycle. So what we're going to do is add these two n-bit numbers using n clock cycles, right? Just basically moving from right to left through the columns of the two operands. So this is really a ripple adder that's spread out in time instead of in space. Right? We do it n clock cycles instead of n stages in space. And by moving into the space domain into the time domain from the space domain, we save on area, right? Because we do things sequentially, reuse this same full adder in this flip-flop over and over again. And as I've said many times, that connection in space between the full adder cells and a ripple adder turn into we need a register here to make a connection in time. Okay, so this takes n clock cycles, uses one full adder, one flip-flop plus registers. If these A and B were streaming, they're coming from some other block which is generating the bits of A and B for us one bit at a time, we wouldn't even need these registers. And if the output was going to another operator somewhere, right, we wouldn't necessarily need to store it. We could just feed that directly into that other operator if that other operator were working in this bit serial way, right? Which means that in principle, depending on the context, you don't even need these registers. So here's an adder. It's extremely simple. It's just a flip-flop and a full adder cell. Right? But, it's slow. This is an interesting concept. People have built computing devices this way, complete computers where they operate bit serially rather than bit parallel, right? Where operands kind of flow around one bit at a time and the operators operate on those bits one bit at a time. So it makes for very kind of small, compact hardware, but the whole thing operates at a rate which is n times slower than if you had parallel operators. But it's an interesting design point, so I thought you should see that. The other thing I wanted to mention is about adders on FPGAs. So the designers of FPGAs have realized that adders are really important. They come up all the time in all different kinds of designs. And if you build an adder with FPGA logic using the LUTs, right, then the carry has to move from LUT to LUT to the connection, whatever means we have for connecting LUTs together, which is the interconnection fabric, right? So because adders are so important, and the most logic blocks for FPGAs include some special circuitry for the ripple, for the carry propagation, the carry ripple really, which connects from cell to cell. So the way this normally works is that the LUTs are used for generating the sum, right? And but based on some results that are the LUTs generate signals that go to this. You think of the LUTs generating the P and the G, and then this circuit here does the carry propagation very quickly. Right, the part of the critical path gets mapped to this hard-coded logic here, right, which goes very quickly. So it's kind of dedicated specifically for doing carry generation. And this gets used for adders, but also for comparators and other circuits that kind of have the same property as adders. So what this means, because of this dedicated logic is relatively small compared to the size of other stuff that's in the logic cell. So it's well worth the expense of putting it into an FPGA. And even though it's not always used, when it is, it makes a dramatic improvement in the speed of addition. So this is from the Vertex 5, which is the one I lectured about, which is kind of an older generation. But the carry in to carry out per bit delay with this dedicated circuitry is 40 picoseconds versus 900 picoseconds if you use the LUT, the F2X delay, which is the delay through a LUT and connection between the LUTs. So that means it can implement a 64-bit adder with a 2.5 nanosecond delay, which is pretty good. So this is why I said earlier, FPGAs typically will use up to about 32 bits. They'll use a ripple adder with this dedicated carry logic. And then for bigger adders, it will use sub adders, which are ripple adders, but then use a carry look ahead scheme to create the carry into each sub block or each sub adder. Okay, so here's kind of wrapping it up for adders. So this is what we looked at. We started with the ripple adder, and that had a cost, which is O of n, and a delay, which is O of n. And we looked at the carry select. And this one had a best case delay, which is O of square root of n, and cost of O of n. And then we looked at the carry look ahead, which used kind of trees. And this also had a cost of O of n and a delay O of log of n. Right? And then finally, I showed you the bit serial adder, which had a delay of O of n, but a cost of O of 1, constant cost. Interesting. If you go back, look at this. Independent of the size of A and B, the cost of this doesn't change. Well, it does if you have shift registers, because the cost of the shift registers scale with n. But if you have just the center part, as I said, imagine these numbers are streaming in and you don't have to have it in a register and you don't have to store the result in a register. If that's the case, then this thing has constant cost. It's independent of n, which is kind of an interesting thing. And in fact, it's an adder that would work for any size n. You have a reset signal, you reset between numbers, and you can add infinite size number. It just keeps going and going and going. It just takes more time. So it has a lot of flexibility that way. So that's why I said cost O of 1. It's not true if you have to pay for the registers. If you have to pay for the registers, then the cost is going to be O of n. Delay is O of n, which is the same as a ripple. It's a little different. In the ripple, the delay is combinational delay. Right? In the bit serial, it's sequential sequential delay. So n clock cycles. For the ripple, it's n units of combinational delay. Right? So if you look at the energy, the dynamic energy for all these is proportional to n, or O of n. It's just pretty much scales with the amount of gates. Now, I did all this in O of n because I'm sure you studied big O notation and you understand what that means, but you have to remember that the O notation hides all the constants. And you have to watch out for this, because the real cost, if you look at it, even though the costs are all O of n, that just tells us how it scales with n and asymptotically what the cost is. But the real cost is something different. The real cost of a carry select adder is at least 2 times the real cost of a ripple adder. We know that because that's the way we built it, right? And the real cost of a carry look ahead adder is probably at least 2 times the real cost of a carry select adder, right? So, the real cost is something times n, and that something, depends on the architecture, and the constants are different here, right? Ripple adder has a small constant out in front times n, and carry select has a moderate size one, and the carry look ahead has, you can see from what I showed you, they're fairly complicated circuits, even though they scale asymptotically as O of n. They have a constant times something times n, which is greater than the other two. So you can fool yourself into if you just looked at the big O notation. Right. So in this these multiplicative constants really depend on the implementation details, like the radix and what type of tree you use and that kind of stuff, and the technology itself, of course. So having said all this about adders, like I said at the beginning of the lecture, it's interesting to look at these because they're designed around clever principles, which may be generally applicable. Practically speaking, you won't have to design an adder. Certainly not in the lab here, because in the FPGA and the ASIC synthesis tools, they will try to choose the best adder architecture automatically. So based on the size of the operands and the kind of constraints that you put in terms of the desired clock period, it will choose an adder architecture that will that could meet that clock period and minimize the cost given that clock period. So that's what it's trying to do. The tool is trying to do for you, and it will do that by choosing from a library of options that it has. So if you this is assuming you specify addition as a plus operator in Verilog, which I presume most of you will do, or you should do. So if you have something like assign A equals B plus C, the tool will take that plus and choose the right adder architecture for you that will hopefully give you the result that you want in terms of delay and cost and power. So that's the final words on adders. Of course, you'll get to revisit some of these concepts in the homework. I'll reinforce some of those as usual. But if anybody has any questions now, we have a couple minutes. Okay. In that case, then I we'll end it here, and I will see you all again on Thursday. And I think on Thursday, then we're going to talk about multiplication, which is also has an equally interesting story. So we'll talk about multiplication on Thursday, and I'll see you then. Okay, take care. Bye-bye.
Sure. Thanks, Professor.
Okay, bye.